Okay, welcome. So what we're going to be covering today is going to be the last topic on waves, and this is going to be largely on, I'll share the notes to show you, but the title of the lecture is Wave Interference and Resonance, but fundamentally what this is about, it's about these two concepts, both interference and resonance. They're related. Um, they're they're related, but resonance is more specific. They're fundamentally about wave interactions. And basically, what we want to know is we want to know want the rules for how multiple waves combine. Okay. So the idea here is that you know in any through any given medium you can have multiple disturbances propagating through that medium, and the question is, okay, how do these waves ultimately combine? And fundamentally the main principle that we're going to be looking at, and the principle that kind of doesn't connect all of them, but all of these other phenomena are derived from this principle. It's the principle of superposition. And fundamentally, this is pretty simple to state, but it has some pretty interesting phenomena, particularly when you deal with periodic waves. And basically, what the principle of superposition says, it says the amplitudes of two, and I'll put this in parentheses, or more waves through the same medium add together. And that is basically what the principle of superposition says. Now, this has some implications. One, your amplitude can be going either up or down, which means that that functionally, if one is going up, one is going down, or it could be left, right, whatever. It means that those will cancel out. However, if they're both going in the same direction, it means that they will combine. They will combine additively, and they'll get larger. And this idea leads to the phenomenon of interference. And interference is something that's observed in any set of waves. Okay. So basically it's that two waves will either combine to amplify their signal, and we call this constructive interference, or to cancel their signal. I should say their signals cancel their signals. And in the case of cancellation, we call that destructive interference. Now, first of all, what I want to show is I want to show I want to show a visual example of this, and then we'll talk about how this implies. Now, I am going to have to shift back and forth between between various between various screens, so please bear with me as I do that. All right, so go to the Desmos screen, and then we'll share, oops, and then we'll share over here. Now, this is the Desmos. This is the Desmos screen right here. If you just look up wave interference Desmos, you'll come up with this. Now I'm going to change the colors. So I'll tell you what, let's make them blue and red, because then it makes sense, right? Then they add blue and red add to give you purple. And that's basically what we're seeing here. So right now we're seeing that the blue and the red, and this is neither, this would be partially constructive interference, but the thing is they're not quite aligned. Okay. So like we can see the purple wave, if we turn off the blue and the red, we can see the purple wave is bigger than either the blue or the red, which are basically the same size. They're just not quite aligned. However, the purple wave is still making it's still making like a wave pattern. And the idea is that this purple wave is some sort of combination, but this isn't as big as they could get. If we line up the blue and the red perfectly, and now the blue is basically on top of the red, that's why you can't see the red. Basically, you have the maximum, oops, you have the maximum construct of interference. So I'm going to take a quick screen grab of this, and we'll just indicate that this is put that over in the notes, and then we'll modify it later. Okay, so that is something that is a kind of interference. So then this was actually, I think A was actually one before, but whatever. We'll leave this one as just sort of our example of neither completely constructive nor destructive interference. And then last thing I want to show is if we can start to see this if we if I drag, I'll use the slider to start dragging them more and more out of alignment. Like from here, you can see that the purple is now down. It's out of phase with both the red and the blue, which are also out of phase, but it's now down to about their size. Okay. But I can even drag the blue further out of phase with the red, and the purple now gets smaller. And right around here, we've minimized our purple. Now I'm going to change this to 3.14159, which is about pi. That's to make basically the A is the phase term in the sine function. And now the red and the blue are completely out of phase. And this would be complete destructive interference. Okay. So that is what we're seeing there when they're canceling each other out, because they're always the opposite. If we go back to to zero, what we see there is we see that at the peak there, that's got a height of 1, but this peak has a height of 2. So basically it's been 1 plus 1 equals 2. If we were to look at this point where it's about 0.5 ish, somewhere around there, then there is about where the purple right above that is around where it equals 1. So basically, it's like the blue has been doubled. It's just been doubled in height, basically. And that's what constructive interference basically means here. Okay. So that I think is just worth seeing what we mean by interference in that context. All right. So I'll stop the share. I'll head back to the notes. This is just so the purple equals the red plus the blue in this case. All right. Now, the idea is that this is just interference. So it's partial. Well, I'll say partially constructive interference in the sense that the resultant is bigger than the two inputs. But here we have completely constructive interference, and that's basically because the red and the blue are on top of one another. It's why you can't see the red in this case. And then this is completely destructive interference. We didn't have one where it was partially destructive, but you could imagine it's close. The red and blue are close to being entirely out of phase, but the purple would have a slight sine wave, but smaller than either the red or the blue. So this is the idea where just by adding these amplitudes together, you can have this sort of weird interference patterns. And if you know some of the rules of trig functions, any trig function can basically be represented as a sine function, and any sum of two sine functions can be represented as another sine function. So that's some of the proof that gets into with trig, but in this case, it's not particularly relevant. You could just do this all numerically and add the waves at this point. Okay, so this is the idea. Now, I want to talk about some applications for this, because one of the most common things, one of the things I like in particular, is anti-reflective coating on my glasses. Now, I just got a really cheap pair that doesn't have the anti-reflective coating, and one of the things that's most I don't want to say difficult, but is most noticeable is what I always see is I always see like just a ghost image of the lights behind me, kind of on the face of my glasses, and basically what that is the lights behind me are reflecting off the glass and then back into my eye. Now, what an anti-reflective coating, when I put those glasses on, I don't ever see that. And the reason is, and we'll get into this a little bit more when we talk about geometric optics, but the reason is that basically what that coating does, it creates a series of reflections that make sure that there's destructive interference going back into your eye from behind you. And what that means, and it also, there's constructive interference going into your eye from in front of you. So that's why you can, that's why it also, it also prevents, um, uh, it also prevents, it maximizes the amount of light coming in from the front. But really, you want the destructive interference from behind you to be canceled, or you want it to be completely destructive interference from the sources behind you. And that's basically what goes on. And what this means is you don't see those images, okay? You don't see those images of the lights behind you. And it's quite noticeable. So if you have the chance to compare that sometime, I definitely suggest it. An example where constructive interference plays in, the anti-reflective coating does a bit of that. But I think the one of the most interesting ones is it's actually like a resonance chamber in an instrument. Okay, and basically what that is setting up a space, for the sound waves to travel, where basically they'll reflect off the edges of the chamber, and then they will constructively interfere with themselves. So if you've just heard, a couple of notes on an unplugged electric guitar versus an acoustic guitar, the acoustic guitar, you get a much richer sound. Like the electric guitar kind of sounds like an electric guitar, but there's not much to it. There's not much body to the sound. It's the resonance chamber of the acoustic guitar that allows the sound to be a little bit richer. So that we'll talk about resonance in a bit, but we're gonna have to discuss standing waves before that. Okay. Because fundamentally what resonance is, it's a phenomenon about standing waves. So put it this way, interference is a sub category of superposition, and then standing waves are a subcategory of interference. So standing waves. All right. Now I'm gonna first give the description of standing waves, and then I'm gonna try and show you an example of an animation of standing waves. So this is two waves traveling in opposite directions that interfere with one another. All right. Now, the point is that the interference with one another. The interference actually goes between, I'm going to use the term deliberately, oscillates between destructive and constructive interference. Now, what this inevitably looks like, it basically means that it seems that the medium is oscillating I'll say while standing in place. And this is why it's called a standing wave. Okay, because in general, waves move. But if you have waves traveling in opposite directions, this can result in an effect where it seems like what you have is just a wave pattern, but it's really just the medium kind of oscillating back and forth, and the medium will do different things. But really, that's kind of what's going on. So I think the easiest way to see this is with a kind of a cool we'll get up here. And I had something on speed of sound. This is okay, so we'll look over here, and then I'm just going to look up standing wave Wikipedia. And you just click on you click on this, and the standard animation they have here is one that I think is pretty cool. So what you can see right here is that the blue and the green, these are just moving. These are two periodic waves that are moving in opposite directions. Now, what the red is the superposition of those two, and you can kind of see it. So when the red gets maximum, that's when the green and the blue are lined up, where they're constructively interfered. And you can even see these little markers here. Make it you can even see these little markers here that are showing that the red and the blue, or the blue and the green, are opposite, so they're constantly adding to 0 at the red. But right here, this is going back and forth between a high and a low, because this is a point where the peaks either meet or the troughs meet, or potentially the two 0 points meet. So that's what we have here. We basically have the medium itself seeming to oscillate back and forth. So the green and the blue would be the traveling waves. The red is the standing wave. Okay, so the red is the standing wave. And what you can imagine that basically what the red is, it's you can imagine that this is an exaggerated version of a wave on a string. Okay. And basically the wave on the string is vibrating back and forth with this. And basically the reason this happens is you pluck that string, it sends a wave down to one end, and then the wave reflects on the other end. It reflects on both ends, and then they start traveling in opposite directions down the spring. Okay. And this traveling in opposite directions is what sets up the standing wave. All right. Now, it turns out only certain standing waves will form in a given medium, and we'll talk about that in a bit. But this is basically what a standing wave is. Now, I want to stop this. I want to stop this and go back to the notes, because we'll need a couple of terms to discuss standing waves before getting too much further. But the idea is that basically what you have here, and do that. Come on. There we go. That basically what you have here when you have a standing wave. The ends will generally be fixed. So these are fixed. Now not always. We'll talk about standing waves where they won't be fixed, but for now I'm gonna view that as the fixed point. Now it doesn't necessarily need to be. Actually, I'll get rid of that because it doesn't need to be. You can't have standing waves just by having two periodic wave sources cross one another. So basically what you have here when you have a standing wave is you have something that, rather than moving to the left or right, what it seems to be happening is you have this dotted line down the center, and then you have these peaks and troughs that seem to be oscillating up or down. So I'll do it in purple. And basically, what you have is you have the black oscillating between the purple. Now, it's not quite what I wanted to do, but that's fine. Yeah, that works. Okay, now when we come up, there's a couple of things that I want to point out. First, I'll mark these in red. The red points, these are called nodes. And these are the points of the standing wave that appear fixed. That appear fixed in place. All right. So that is a node. And this particular standing wave has 5 nodes that I've drawn. So there are 5 nodes in this particular one. Now, switch to green here. Then we have these points right here. And I'm drawing them on both the top and the bottom, but you got to remember, in the standing wave, it's not at the top and the bottom. It's either one or the other. So basically, these green points are called antinodes. All right. And basically what the antinode is, this is the point of a standing wave that oscillates between, and really what it's doing, it's oscillating between a peak and a trough. Okay, that is fundamentally what a standing wave is doing. All right, so that's what's going on with standing waves. Now I'll just make a quick note. Standing waves can result from wave reflections in a single medium. In fact, this is how most standing waves come up. It's generally not because you have two different sources of waves sending them in the opposite direction. It's generally what you have is you have a reflection on one end that comes back and interferes with the original wave. Okay. Or if it's a periodic wave, it interferes with a later portion of the wave. All right. That is what is going on with standing waves. Okay. So that's something to keep in mind. All right. Now I want to just talk about some of the images associated with standing waves. So I'm going to do this in different colors. All right. So this first one, this is called the fundamental. Actually, tell you what, let's talk about let's get to resonance before we talk about that, because I think when you can have standing waves without having really a fundamental, when you start talking about fundamentals, that's a resonance condition. So resonance, this is a condition in which wave reflections of an existing medium, actually, obviously of it, we'll just say of a medium, sorry, in a medium, result in standing waves in that medium. Okay, so this is basically what's going on with a wave on a string. So for example, you wave on a string. And the idea is that fundamentally what you can have, so we'll just have this, tell you what, we'll have it be black, and it's just, make it a little bit longer. It's just got this length L, but here we have no wave. All right. So that's our first one. It has a length L. Now, what you could do is you could start vibrating this string such that a standing wave formed. Now, the main condition of the standing wave is that the ends are fixed if it's a wave on a string. It's not the only condition, but basically, if you think about like a guitar string, that string can vibrate any which way, except for the fact that those ends have to be held in place. Okay, at the peg and at the base, I don't remember if it's called the board. I don't remember. But at the two ends, the string is held in place, and then it can vibrate a number of different ways. But fundamentally, at the ends, the string has to be held in place. And what this is going to do, this is going to limit the possible wavelengths that this string can have. Okay. So the first one I want to talk about is oops, that's very bold, is the fundamental. And basically, tell you what I'm going to do. I'm going to do dotted line. I don't want them to be red. I want them to be in black. I'm going to do a dotted line all the way down. And maybe we'll have to go further down than that, but that's okay. And basically what the fundamental does, it oscillates. So the ends are still fixed in place, but basically what you have is you have a single peak that oscillates back and forth between a peak and a trough. Okay, so this isn't even a full wavelength. As a matter of fact, in this case, what we have is that our L is only equal to our lambda over 2. Okay, so that's only half of a wavelength. If we wanted a full wavelength, we'd have to, we'd have to draw the other half of that cycle. Now, another way to say that, lambda is equal to 2L. It's worth noting. In here, the number of nodes we have 2. And then antinodes, there's only one antinode in the fundamental. Okay. Now, the frequency is going to depend on the speed of the wave. In the wave on a string, it turns out the speed of the wave is dependent on the tension. Okay. So that's something worth remembering, that while the wavelength is determined by the length of the string, how the frequency is also dependent on the tension. This is why when you tune you tune a guitar or any stringed instrument by tightening the string. You're changing the wave speed, which changes the frequency, and the frequency is what we hear in the tone. Okay, the wavelength is unchanged. All right, so that's what's going on with that. Now, next one to look at, change to purple. This is gonna go, I'm gonna call this the second harmonic. And basically what it is, it's basically the next wave that fits in this system. And what I mean by fit is, I mean those ends have to be nodes. Okay, the ends have to be nodes. So and that's, I'll even put that up here, is that the ends are nodes. And it's not just they are nodes, they must be nodes. No other frequencies will fit here. Okay, so we put this on the end here, and I won't draw the amplitude as big, but basically that is the next one. So that is a full wavelength. And what this thing is going to do, it's going to basically oscillate. You're going to have 2, so you have a third node right there. So we have nodes 3, but 2 antinodes now. Okay. And then your length is then equal to just one wavelength. So obviously lambda is equal to L in that case. Okay. So this is what your second harmonic would be. Now I'll go up to, I think, probably just the fourth harmonic. We'll go with green next. So we'll do the third harmonic. All right. And I need to, does take a little bit of planning. Sorry. And again, it's not perfect, but you get the general idea. Okay. So this thing is now going back and forth between these areas. And we now have 4 nodes. For antinodes, there are 3. Actually, I'll probably just stick with this one. And then the length is equal to, well, it's actually 1.5 wavelengths. So a full wavelength would be right there. So that's a full cycle between right there. And then there's another half cycle. So this would be 3 over 2 lambda. And then lambda is then equal to 2/3 L. And you might start to pick up a pattern here. It's that ultimately your length is going to be n lambda over 2, where n is just some integer. Okay. So in the first one, if n is just 1, that's what that, that's where we get L over 2. If n is equal to 2, that's going to give you the second harmonic. N equal 3, that's going to give you the third harmonic. So another thing worth indicating here is that n is equal to 1, n equal 2, and then n equal 3. So these basically the reason I did this, the fundamental could also be called the first harmonic. But that corresponds to the number that we would put into this formula to find the wavelength based on the L. Now, to briefly discuss, when you pluck a guitar string, you often will have a mixture of harmonics. However, I believe, actually, I don't remember. I think it's the fundamental that the string primarily vibrates with, but you can get a mixture of harmonics. And this is actually one of the ways that you can actually tune a guitar. you can listen for some of those higher order harmonics. In any event, that is what I wanted to show about that one. Now, another way you can have resonance is with an empty chamber. And the common way I've done this is if it's open in two spots. And in many ways, this is how in some ways this is how woodwind instruments work. Now those are somewhat not open in multiple spots, but in and they're kind of mixtures. Like it's not pure, but in any event, what you can imagine is that if you just had a long tube, like a PVC tube, and you can actually set up resonance waves within a PVC tube. We're going to be doing something similar in the lab, but you can actually set up resonance waves. I'm going to change this slightly. I want it to be bigger and not quite as long. So basically, what you have now is you have open ends. Now, the only way this changes is that you need antinodes at the ends. Okay. All right. Now, the idea here is that I'll just do the dotted line again. And I'm gonna kind of go through this one quickly, because it's not too different than what we just saw. Changing that. But the first harmonic, the fundamental, so going back to red, basically what we have here, the way we get this is we'd start at, say, the bottom or the top, doesn't matter, at one end, and we get to the other end there. So in this case, we have the nodes we have are 1. We have 2 antinodes, and then our lambda is equal to 2L again, or L is equal to lambda over 2. Okay, so this is still just half a cycle. It's just a different half of the cycle. It goes from trough to crest. Now remember, a full wavelength would be crest to crest or trough to trough, so it's only going half that. So that's one way to think about that. Now for the next one, I think the next color I did was what? It was purple, yeah. For the, and then again, that's the fundamental. Now this next one is actually it's gonna start at either the top or the bottom. I'll just start at the bottom. And it's gonna go, and then on the other side, it will meet at the bottom. So here we again have lambda is now a full cycle. And we have, for the nodes are actually going to happen there. It's a little difficult to tell where they happen because they're not fixed, but the nodes will actually happen at that point. And then we have antinodes at both of the ends and one antinode in the middle. So we have 2 nodes and 3 antinodes here. All right. And then the next one to see, so it's going to go, say, kind of like so, and then finish up at the top. So in this case, what you have here is we have a full, like from there to there, again, that's a full cycle. And then it goes from trough to crest again. So our length is equal to 3 over 2 lambda once again. So lambda is equal to 2/3 L. So this actually ends up being the same thing. And the number of nodes we just have 2 nodes. We have 3 nodes. I'll indicate that. The middle line, basically, it's where the standing wave crosses the middle line. And then we have 4 antinodes. Okay. So this time, the harmonic number, again, it would be n equal 1, n equal 2, and n equal 3. The harmonic number corresponds to the number of nodes, but in any event, the math is fairly similar. Now, it's the last one where the math changes. And this is one end open, one end closed. So an example of this, I think a woodwind instrument is a better example of this, because what fundamentally what you're doing when you blow into one end, you create the vibrations into one end. you're not just kind of sending them down, but you're also blocking off that end. Now there is a little bit of fungibility there, but fundamentally what this means is basically you would have like one end of the tube blocked off, and I'm not going to make that quite so long, but it would look basically like this. Okay. So again, going back to the fundamental, what we have here is, and I'll just indicate what we need. We need a node at this side, and we need an antinode at this side. Okay. And though that is what is going to dictate what fits into there. Now, what this means, we're going to need that node, and we could, could be the top or the bottom. So basically what this wave, it's going to oscillate between those two positions, the solid line and the dotted line. All right. Now, in this case, what we have is the nodes we have just one. The antinodes are also just one of each now. But what's interesting now is that my length is only, actually, we'll continue to do that in red. My length is only equal to lambda over 4. Okay. It's not equal to lambda over 2 this time. All right. So what this means is lambda is equal to 4L. All right. So that's what's going on there. Now, when we go to the next one, again, going to purple, what we have now, it's going to look something like this. Now, it turns out that that is not even a full wavelength yet. The full wavelength would go a little bit beyond because we would need to get back to the node position, but we don't. We only have 2 nodes, and we have 2 antinodes, and we're not yet, the length is not equal to a full wavelength. It's actually equal to 3/4 of a wavelength. So if we solve for lambda, this would be 4L over 3. All right. Now, to get to one more, do one more. Again, we'll get to the third harmonic. Red is first harmonic, purple is second, and green is going to be third. All right. So, whoops. Green. There we go. And now what we have here is we have something that looks a little like, no, that's not quite right. Like that. All right. And so what we have here is we do now have a full cycle. So we have a full cycle plus actually an extra quarter cycle, because again, it goes from a node to an antinode there. So that's a quarter cycle. So our L is now equal to 1 full cycle, which is 4/4, plus another quarter cycle, which will be 5/4 of a wavelength. So again, you can solve for lambda. That would then be 4L over 5. Okay. So that's kind of what's going on there. And the nodes we have, you can count those. There are 3. And you probably guess that from the pattern. And same number of antinodes. Could probably guess that from the pattern as well. All right. So this one, in this case, what we have is L is actually equal to N lambda over 4, where N is odd. Okay. And this is one of the things that makes it a little bit more difficult, is that in your third harmonic, on your first harmonic, no problem, it's still just N equal 1. But in your second harmonic, now it goes to N equal 3. Okay. And in your third harmonic, it now goes to N equal 5. Now, for this reason, we don't actually call these the second and third harmonics. We call them the third and the fifth harmonics. All right. And the whole reason is just so that this number here, whichever number you're dealing with, matches the harmonic number. So when you have an open and a closed end, you don't have any even harmonics. Okay. Now, sometimes people, they say that they do, but and you could rewrite this formula in a different way. Like the actual formula, if you wanted to just go first, second, third, it would be 2n minus 1 instead of n. And 2n minus 1, that will just give you odd numbers when you plug in 1, 2, 3, 4, so on and so forth. So that's how you can get that to work. But this is the formula that the lab uses, so it's the one I'm going to present here as well. Okay, so that is what is going on. Now, again, when you do this in the lab, basically this is going to be your goal. What you'll do is you'll find these resonance points by listening. So you'll record values of L by listening. From those values of L, you'll calculate your wavelength. And then from your wavelength with the frequency, because the frequency will basically be your independent variable, with the wavelength, you can then calculate the wave speed. Okay, so that is going to be the goal. Now, last thing I wanted to talk about briefly is beats. Oops. So basically, beats are an interference phenomenon that occurs when slightly different frequencies mix. Okay. And you can actually demonstrate the phenomenon of beats pretty readily. It's kind of cool, and this will work with any speaker, any tone generator. You can do this. But what I'm going to do is I'll show you what I mean. Now, first of all, what I want to talk about is the frequency, the F bar. This is just the average of the two frequencies, and it's basically what you're going to hear, assuming they're of equal volume. If they're not of equal volume, it's a little bit different, but so average of two frequencies. All right, so if you're mixing two frequencies, basically the overall sound you'll hear is just kind of an average of those two. However, you will also get an F sub B, which is your beat frequency. And what I want to talk about what the beat frequency is, but I think it's helpful if you observe it first. So that's what I'm going to do first before I go do that. All right, so I'm going to find my tone generator. Oh, there it is. Oh, so many windows. Okay, so all right, now I'll share with my other thing. All right, so what I have here is I just have two browser windows with the same tone generator. Now, what I can do is I can play, if you play this, hopefully you can hear it from my speakers. You can just hear a 440 tone. Increase the volume a little bit. Okay, so that's just a 440 tone. Now I'll stop that and I'll change this one to 444. And it's very difficult to distinguish between the two. Maybe some people can. I certainly cannot. All right. Now, one more thing. I'm going to go back, play this, play the other one. It just gets a little bit louder because it's got two sources now. But I'll stop both of them. Change this one back to 444. And what you can hear that modulation, that kind of change in the volume between the two sounds. That is the beat, and that's happening. You might be able to time it, you might not, but that is happening about 4 times per second or at 4 hertz. Now I'll prove that by, we'll turn this one off and we'll change this to 442. Notice it slowed down. You can still hear the beat, but it's slowed down. Stop it, change it to 441. Much slower now. Now it's taking about entire 2 seconds to go through a single cycle of the beat. Okay, so this beat is a modulation in the amplitude. Now I'm going to stop these because I find the beeping annoying, but we'll go back to our interference. Okay, so this is our, oh, I think I actually, whatever, it doesn't matter. Yeah, this is a different window, but whatever. Okay, so we'll do blue and red, and they mix to purple. Now what I'm going to do here is instead of having, I'm going to do, instead of just having them both be the same frequency, I just multiply the X by something in there, and this changes their frequency ever so slightly. All right. And, whoa, that's cool. And what you can see, well, dang it. And what you can see there you go. What you can see is hopefully what you can see is that the interference pattern, which is the purple, basically what the red and the blue are doing, they're changing their alignment ever so slightly over time. And what the purple, if we turn this off, what we can see the purple's doing, it's oscillating with roughly the same frequency. Now, it'll be the average of the two frequencies, but it's oscillating with roughly the same frequency. But what is happening to the amplitude is the amplitude is going up and down with its own periodic signal. Okay. And this idea of the amplitude going up and down, that is what we mean by the beat. Now, in sound, that's why we hear that raising and lowering of the volume periodically. That is the beat frequency. Okay, so that's what's going on there. So I'm just going to go back to the notes and finish up that. And basically the interference phenomenon is that you get a volume or amplitude modulation in the beat frequency. And what I mean by modulation is I just mean that changing in volume periodically in the beat frequency. And the beat frequency is just the difference of the two frequencies. Okay. So difference of two mixed frequencies. All right. I think beats are a pretty cool thing. There are a lot of really cool wave phenomena that we just don't have time to cover, but I think beats are kind of interesting. So it's just the second frequency minus the first frequency. Okay, so I'm going to go ahead and cut things there. Thank you for joining me in the lecture today, a bit longer, but I really do appreciate you sticking with me to the end.